Okay, maybe we can start. Welcome everyone to this edition of the RESANET webinar. Today we have the pleasure to have the talk of Hugo Jacob, third year PhD from IJCLab Orsay, who is going to present us his PhD work titled Proton-neutron pairing in the FPS shell via the chromium-48 proton-induced helium-3 46 vanadium transfer reaction. So, Hugo, whenever you're ready.
Okay, thank you for the introduction. And thank you for giving me the opportunity to talk about my PhD topic for this webinar. So, as Tanya said, my topic is to study proton-neutron pairing using a 48 chromium P-helium-3 46 vanadium reaction. So, I will start quickly with an outline of this presentation. So, first, I will talk about the scientific motivations that led us to do this experiment. Then, I will go through the experimental setup, some features of the data analysis and some simulations. And then I will show you some preliminary results that we recently got for this experiment. So first of all, the scientific motivations. So we are interested in studying proton-neutron pairing. So first of all, what is it? So you may all be quite, used to pairing, but usually we are more used to the proton-proton and neutron-neutron pairing effects that we can see right here. These two types of pairing are what we call isovector pairings because they are only available in the configuration spin equals 0, isospin equal 1. But us, we're interested in the proton-neutron pairing, which is a pairing between a proton and a neutron. And this type of pairing is available in two different channels. The isovector channel, so same as proton-proton and neutron-neutron pairing, but also another channel that is not reachable with the same particle pairing, which is isoscalar pairing, spin equal 1, isospin equal 0. Why is this kind of pairing more exotic? Because pairing requires an important overlap of the wave functions. So naturally, proton and neutrons are in the same shell, so it's easy to do proton-proton or neutron-neutron pairing. But to have an important overlap of the proton and neutrons, you need to be in or very close to n equals z nuclei. So it means that only this nuclei can show this kind of effects, so there are not so many. And the idea to study this proton-neutron pairing is to try to understand which pairing strength is the strongest. For instance, we could think about the most simple proton-neutron system, which is the deuteron, simply one proton, one neutron. And we can see that the deuteron is only bound in the isoscalar channel. So there is only the ground state spin equal 1, isospin equal 0, and the other states are not bound. So it's already an indication that maybe isoscalar pairing could be stronger than isovector pairing. And as pairing is a collective effect, the idea is to study the collectivity of this pairing, and so also to study it in the biggest shell possible because it should show the maximum effect as big as the shell is. So to give some example of how we could try to understand the pairing, so you may know that since pairing is a collective effect, it increases the binding energy of nuclei. So we see that, for instance, in the difference of binding energy of odd and even nuclei. And here what I'm showing is an example of the binding energy anomaly in n equals z nuclei. So you can see that here what I'm showing is a difference of binding energy that we get by adding or removing a neutron-proton pair. So it's kind of showing the excess of binding energy coming from the addition of removal or of a proton-neutron pair. And you can see that this value is systematically more important for n equals z nuclei that I'm showing here in red. So it's already giving us hints that maybe in this n equals z nuclei, there is this proton-neutron pairing that is playing an important effect to explain the binding energy of this nuclei. Okay, and so how do we want to study proton-neutron pairing? There are several ways to do it, but the way we chose to do it is to use the two-nucleon transfer reaction. Why two-nucleon transfer reaction? Because it is predicted that pairing effects, the collectivity of pairing, should increase two-nucleon transfer cross-sections. So here I'm showing an example of any shell that you could imagine. So here it's the closed shell. So since there is no collectivity when the shell is closed, we expect the cross-section enhancement to be the reference, like 1. Then as we add pairs to closed shell, we start to have some vibrational increase of the cross-section, so increase that is kind of linear. Then as we reach the middle of the shell, we can maybe see some phase transition to a superfluid condensate. And this cross-section enhancement would be proportional to pairing strength and also shell gaps. And as we go down to the other shell, to the next shell, there is kind of the symmetry between particle and hole. So we expect to have a decrease, which will be again vibrational. And so the idea is that we want to study that for proton-neutron pairs, but we already have examples of this kind of experiments that have been done for neutron-neutron pairs. So here I'm showing now some examples of what has been done in the past for neutron-neutron pairs. A good example is, for instance, lead-208, because lead-208 is a double shell closure, and some other lead isotopes are stable. And so the idea is to transfer neutron-neutron pairs. So we go from lead-208 to lead-206, lead-206 to lead-204, etc., etc. And here it's what is done. So you can see lead-208, lead-206, lead-204. And what we are doing is we are comparing the first 0+, which is the 0+ of pairing, to the second 0+, which is not a pairing state. And we expect the first 0+ to have an increased cross-section, but the second one to stay the same. So we do the ratio of cross-section to compare these values. And we see that the second one is staying the same, but the first one is increasing. Since we do the ratio of cross-section, we see that we have this linear increase of the transfer cross-section for lead. And then we can also take the example of tin. We have, so now tin isotope is closed shell in proton, but is in the middle of the shell in neutrons. And since it's in the middle of the shell, we expect to have more like a flat behavior of the cross-section, like kind of superfluid condensate. And that's what we see here. So we do the same ratio of first 0+ to second 0+, and we have this very nice kind of parabolic behavior, quite stable. So it gives hints that probably it's a superfluid behavior of neutron-neutron pairs at the middle of the tin isotope shell. Okay, so we are showing that for neutron-neutron pairing, we seem to have some effects that are possible to probe with two-nucleon transfer. And so what we're interested in is doing cross-section ratios, but now we want to do cross-section ratios between the two different types of pairing. So now we want to do cross-section ratios between the isoscalar state and the isovector one. And the idea to do that is to use the p-helium-3 reaction, because its selection rules allow to populate both low-lying states at the same time with the same reaction. So the idea is to start from an even spin equals 0, isospin equal 1, isospin equals 0 state, and then to transfer and to go to the isovector isospin equal 1, spin equal 0, and also to the isoscalar isospin equal 0, spin equal 1. And then when we do this transfer, we want to see the ratio of the cross sections to see which one is stronger in this nuclei. And so here I'm showing some results that have already been, some experiments that have already been done in the past to study exactly that. So here you see that the value here is the ratio between the isovector state and isoscalar state, two-nucleon transfer, proton-neutron pair. And there it has been done in the SD shell. So you see that here you have shown the superfluid limit, here the single particle limit. And we're interested in doing it in the F shell. So again, two-nucleon transfer. And here I'm also showing some results that have already been done in the F shell, so in the nickel 56 and iron 52. And the nucleus that is interesting for us is the 48 chromium, which is here at the middle of the F shell. So since we are doing it at the middle of the F shell, we expect to see some kind of superfluid behavior as what we saw for the tin isotope. So pairing in the F7 half shell. So what is specific about F7 half shell and what do we want to study pairing here? So we have shown that already in the previous shells, this kind of studies have already been made. What is interesting in F7 half shells is also that there is kind of a change of trend for proton-neutron pairing, most likely. Here what I'm showing is the difference of binding energy, the difference of energy between the first 0+ and the first 1+, corresponding to the first isoscalar and first isovector states. And you can see that systematically for low masses nuclei, the 1+ is systematically below in energy. So it means that it's more bound. And you can see that as we progress to the F7 half shell, in the F7 half shell, the lowest state is systematically the isovector one. So there is already an interesting change of trend. It seems that at the beginning for low mass nuclei, the isoscalar state is more bound. So there is kind of more isoscalar strength. But then as we reach the F7 half shell, the isovector one seems to become again stronger. So this is also predicted in some calculations. Here I'm showing some results of these papers that try to see the pairing strength ratio by matrix element in the FP shell. So here the value that you see is kind of a strength ratio between isoscalar and isovector. So if it's above this line, isoscalar is stronger, and below the line, isovector is stronger. And so what we see is that when we add the partial wave beyond 1s0, it tends to favor a lot the isovector channel, which is already a hint that probably in the F7 half shell, the in-medium nuclear forces have an important role. So maybe it's not as simple to say that the pairing effects are simply, we can ignore in-medium effects for pairing forces. And another thing that we are interested in studying is to study the interplay between pairing and deformation. Because as we can see on the left here, I'm showing some calculations that are done with HFB models for nuclei that are heavier than the nuclei we are studying, but it's still interesting to see the effect that it has. So they did a first calculation using HFB model with neutron-neutron, proton-proton, and proton-neutron pairing forces. And they are trying to see if the isovector or the isoscalar force is dominating. So in red, it's isoscalar dominating. In green, it's isovector dominating. And we see that when we have kind of a toy model without deformation, you can see that most of the time isovector forces are dominating, but in some regions, we have some isoscalar forces that start to be important. But then as we tune realistic deformation, then it completely changes the configurations, completely changes the correlation energies, and it changes the nuclei that could have isoscalar or isovector pairing. So already deformation can play an important role on pairing forces. I'm showing here the n equals z nuclei of the F7 half shell. And as you can see, I'm showing the deformation, of this nuclei. And what you can see is that 48 chromium is just here. It's in the middle of the shell. And it has a very strong deformation, much more important than the other nuclei. And it's predicted that this deformation could affect a lot the T=1 channel. So here it's shown a calculation that was made by Danilo Gamba-Curta and Denis Lacroix. Try to do a calculation of deuteron transfer probability, so what we are looking for in this experiment. And we can see that the T=0 channel should stay almost the same, but the deformation of 40 chromium is around here. So the T=1 channel should go down a lot because of the deformation of 48 chromium. So we expect to see maybe already we see that maybe we have less T=1 strength in the F7 half shell, but maybe we have even less because of the deformation of 48 chromium. So there's an interesting interplay of both effects to study in this nucleus. Okay, so now that I gave some insights about the scientific motivations, I will go through the experimental setup of the experiment. So this experiment took place in the Mugas-Statly's campaign at Ganil. So we need a 48 chromium beam at 30 MeV per nucleon. This beam was produced by fragmentation of 50 chromium and selected by Lee spectrometer at Ganil. And this beam was impinging on a 5 milligram per centimeter squared CH2 target, so to get the protons of the hydrogen. So you can see here a picture of the experimental setup. We have two CATS MWPC detectors to detect the beam and reconstruct event by event the beam position on target. We have 4MUS2 detectors, which are light particle detectors, light charge particle detectors to detect the helium-3s. We had a set of 12 exogam germanium detectors to detect gamma rays because it was important for this experiment to have gamma rays to be able to identify the state of interest, this 1+, very close to two other states in energy. And we also have a 0 degree detection to detect the beam-like nucleus and to be able to identify it and to have a better signal over background ratio for this experiment. Okay, so first of all, the beam tracking with CATs. So CATs are MWPC gaseous detectors. The charges, when the beam crosses the detector, the charges are collected on the wires. And we use two CATs to project the position of the beam on the target. So we have a 1 millimeter resolution position on target, and they can handle a maximum intensity of typically 2 × 10⁵ particles per second, which were typically what we were running with in the experiment. Then we have the targets. So we have a target frame holding up to 5 targets. We used 2 CH2 targets in case one was breaking. We also used 1 empty target and 1 carbon target for background runs. And we also used a mask target to be able to check the CATS reconstruction on target. And here I'm showing, for instance, what we had during the experiment. So this is basically a reconstruction of these holes in this target mask. So it was done to check that we have a good reconstruction with CATS and that we know exactly where we are on the target. For the light particles detection, we use the MUGAST array. So the forward part is the 4ms2 detectors, so which are 1 DSSD plus 16 CSI crystals behind, as you can see here. They were put at angles between 5 and 25 degrees, and we can identify particles depending on their energies. We can identify them by E time of flight or delta EE in DSSD and CSI. And as you can see here, we have an example of how to identify particles in delta EE. So we have proton, deuteron, tritons, helium-3s, and alphas. So thanks to that, we can just make a cut on helium-3 particles and identify the reaction of interest. And then at backward angles, they were not used in this experiment, but just to show the full MUGAST Atlas setup, we have 5 trapezoid, MUGAST trapezoid, which are simple 500 micrometer DSSDs. They cover angles between 105 degrees and 160 degrees. And we're able to identify particles at backward angles with E time of flight particle identification, what you can see here, so proton, deuterons, and alphas on this plot. We also have the 0-degree detection to identify the beam-like nucleus. So the 0-degree detection covers angles between 0 degree and 2.5 degrees. And it's made of drift chambers, ionization chambers, and plastics. The drift chambers are used to get the angle of the heavy recoil. And with the ionization chambers, we can get the charge with a delta E. And the plastics are used to do delta EE or delta E time of flight to get a nice recoil nucleus identification. Here I'm showing some examples of what we had during the experiments. So these examples are done with cocktail beams and lower intensity, but here you can see that in delta EE, we are able to identify the several Z and masses of the nuclei. And we are also able to identify the nuclei by delta E time of flight, as shown on this plot. And finally, to identify the gamma rays, we use the exogam array. So we used 12 exogam germanium clovers that were put around the reaction target. We used this to do the in-flight spectroscopy of the target-like nucleus. We had around 5% efficiency at 1 MeV, and these crystals are segmented for better position sensitivity, which is important for Doppler correction. Okay, so now about the data analysis. So first of all, what was important is that this experimental setup was running basically in a timestamp, which was new for the MUS2 array. So the data were merged in a 6 microsecond window, which is too wide to avoid random coincidences. So it was, first of all, important to select the timestamp prompts for all the detectors. So here I'm showing, for instance, a timestamp difference between MUS2 and the plastic detectors. So we have a prompt, but we also have a lot of random coincidences coming in. And here I'm showing an example of how this analysis works, which means that by selecting the MUS2 exogram prompt, I'm able to remove 7% of random coincidences that we had during the data. So first of all, it's important to remove these events that are not prompt and to do a good timestamp selection. Then the second step is to have a good 0-degree detection identification, because here I'm showing a plot that we have in 0-degree detection in delta E time of flight when we select an helium-3 in MUS2. And we see that here we have some random coincidences of chromium beam. We also have vanadium, which is what we're interested in this reaction. But we also have, for instance, titanium that can come from the breakup of helium-3. So what we want is to be able to select vanadium and helium-3. So we are sure that we have the good reaction channel. And the beam transmission is around 80%. And we got, at the end of the day, around 37% efficiency for this 0-degree detection, which was a bit of a problem for the statistics. Then I performed an exogram Doppler correction. So I used a new method that I implemented in NPTool, which takes into account the depth of interaction of the gamma ray in exogram to be able to reconstruct as well as possible the position of the gamma ray in the exogram array. And we are also using the two-body kinematics of the helium-3 particle. So with the helium-3 energy and angle, I'm able to infer the energy and angle of the heavy nucleus. With these two information, I'm able to have the good angle between the nucleus and the gamma ray and to have calculated beta event by event. So by using all this information, we're able to have a good Doppler correction, which we use to separate well the peaks that we have. And in particular, it's important to have a good Doppler correction because the two peaks that we are, the gamma ray that we're interested in is at 1 MeV here, and there is one that is quite close in 915 keV. So it's important to have a good Doppler correction to be able to separate well these two states to evaluate our cross sections. And then we are reconstructing the kinematics of MUS2 using the kinematic line and to reconstruct the excitation energy of the heavy recoil. So here I'm showing the P-helium-3 reaction selected with 0-degree detection and selected with an helium-3. And you see here it's the ground state kinematic line, and we have other states above in energy. And here I'm showing what we get when we reconstruct the excitation energy of 46 vanadium. And we see that here we are able to separate well this ground state. So ground state, we can only have it with excitation energy. We are able to separate it from any other states. So we are happy because we can fit it and get the cross section. And then we have this big bump in which there are a lot of many different states, but it's okay because we can identify them using their gamma rays. So we are confident that we will be able to get the cross sections for these states. Then to evaluate the efficiencies of this experiment, I used several simulations. In particular, I used NPTool, which is using the Gen4 software to perform simulations of the experimental setup. Here I'm showing a Gen4 simulation of MUS2 here, the 12 exogam detectors, and the 0-degree detection. The idea is to evaluate not only the geometrical efficiency, but also the software efficiency. What I mean by software efficiency is, for instance, the efficiency that we lose when we do matching of events in MUS2 or when we do selections in ZDD, etc., etc. And so I was able to simulate the real Doppler correction and real reconstruction of events with MUS2. So here I'm showing some simulations that were done. And I'm showing also that we're able to reconstruct proper excitation energy E gamma matrices. And you see that here, the states, we cannot identify them with their excitation energy, but with their gamma rays energy, we're able to separate them nicely to evaluate the population of the states as well as we can. Okay, and now I will show you some preliminary results that we got for this experiment. So how do we fit the final data? So here I'm showing again the excitation energy spectra that we got. So we have here this ground state. This excitation energy fit is only used to determine the ground state amplitude. The rest we get it with the gamma ray. And here I also show the fit of several other states. So we have the 3+, which is isomeric, the 2+, the 1+, and another 1+. And this 1+ corresponds to this gamma ray that I evaluate the amplitude by fitting this gamma ray and tuning it in the excitation energy. I also fit this 1+ and this 2+, and I also put the amplitude in this fit. So basically, the only three parameters are the amplitude of the ground state and the isomeric state. And so we see that up to 1.5 MeV, we have a nice fit, which makes us quite confident that we have a good reconstruction of the ground state amplitude. And here, so the state of interest for the isoscalar state is this one, the one at 1 MeV. And I'm showing that here we are able to separate it well from the 2+ at 915 keV. So we are confident that we also have a good estimation of the cross-section for this one. And so the preliminary results, so this plot is a plot that was made in the previous paper for 56 nickel and 52 iron. So here I'm again showing the ratio of cross-section between the T=1 channel and T=0, so isovector over isoscalar. What is shown here in red is some DWBA calculation with GXPF1, which is an interaction that should take into account pairing interactions and also a deformation that is not completely realistic, but it takes into account some part of the deformation. And here in blue is shown just single particle, purely simple particle configuration plus DWBA. We see that for 56 nickel and 52 iron, the points seem to follow a bit the red curve, even if the error bars are a bit important. But we see that for 48 chromium, the preliminary results that I obtained is extremely close, is even compatible with the single particle plus the WBA configuration. I'm also here showing some preliminary results for absolute cross-sections. These results are quite recent and are still very preliminary, but we expect them not to change too much. And we can see that here, even the absolute cross-section for the isovector state, if we compare it to what we had in previous experiment for 56 nickel and 52 iron, we see that it's systematically lower. We see that we had kind of an increase of the cross-section here, and now it's much lower than what we had in the past. So what we see here, how to interpret these results, it seems that in this 48 chromium, probably deformation plays an important role in hindering a lot the isovector channel, at the point that probably both isovector and isoscalar pairing channels are extremely, their strength is probably very low in this 48 chromium. So the explanation that we have is most likely it is because of the important deformation of this 48 chromium. And that's it for me. Yes. So thank you for giving me the opportunity to give this talk. And if you have any questions, feel free.